All right, so a lot of you guys are having some trouble with getting the actual pages that it's printing out at different pages. You can always copy and paste from that original document, make sure it's set up the right way. This is the start of this acid-base neutralization and titration assignment. That's why I put the headings on there: acid-base neutralization and then titration, so that you know exactly what you're doing here. So if you've been keeping up with everything since, you know that acids neutralize bases and bases neutralize acids. If these are strong, for example, we have HCl and NaOH. If they're strong, then we would get salt and water. NaCl plus H2O. Now this salt is the salt that we call table salt. Well, in reality, table salt has a lot more stuff in it, but sodium chloride is one of the major ingredients in what we call table salt. It doesn't mean that it has to be sodium chloride. You could do the same thing with HCl and calcium hydroxide, or HF and sodium hydroxide. Then you would get sodium fluoride, which is found in toothpaste and in water, and water. But that's the idea of this acid-base neutralization. Basically, the H and the OH make H2O, and then everything else is a salt. This can occur with weak acids and bases as well. They just do it a little bit different. For example, that proton that moves around gets picked up by water, or an OH will pick up a proton or a hydrogen ion from something else, and that neutralization will still occur. And so, as it says here, scientists use a procedure known as titration to determine the concentration of an unknown acid base by using a known concentration. So if you don't know the concentration of one, but you know the concentration of the other, then you can figure out the opposite. Quite simple. So if we take a look, when you do this, you actually use what's called an indicator. And that indicator basically turns color at some point, which we call the endpoint. And then we can do our calculation based on that. So let's take a look here. How many moles of KOH are needed to completely neutralize 1.56 moles of phosphoric acid? So we want to start off by writing out a balanced equation. This is going to bring us back to our early days, where we need to understand that this is a double replacement reaction. So potassium is going to come in and replace H. H is going to replace the OH. Remember, this 3 doesn't necessarily go with that. We figured that out by charges. And we hopefully know at this point that OH has a -1 charge. So since OH has a -1 charge, that means we're going to have 2H or H2O. Or HOH, because H has a +1 charge. Now for this potassium phosphate, we know that phosphate actually has a -3 charge. When we look at our periodic table, we find that potassium has a +1 charge, so that means that we have to have 3 of these. So let's take a look here. We have a 3 case here, that means we need a 3 here. That gives us 3 H's plus 3 H's, which is 6 H's. So we need a 3 here. We have 1 PO4, 1 PO4. We have 3 O's. We have 3 O's. So there we go. We have a balanced equation now. Now we can use dimensional analysis, just like we always do, to solve this. We start with 1.56 moles of H3PO4. H3PO4. So what has to go on bottom? Well, every 1 mole of H3PO4 reacts with 3 moles of KOH. So then it's simply 1.56 times 3.
The answer is 4.68.
4.68 moles of KOH are required to neutralize 1.56 moles of H3PO4. That's that dimensional analysis we've done all along. We do the same thing with that with 2. Same way. Let's take a look at 3. How many milliliters of a 0.45 molar hydrochloric acid solution must be added to a 25 milliliters of 1.0 moles of KOH to neutralize it? Well, we make our balanced equation, HCl plus KOH yields H2O plus KCl. We check to make sure it's balanced, and it is. So now we can start with what we have. Well, we want how many milliliters? So that has 1 unit. This has 2, and this has 1, and this has 2. So we're going to want to start with that 25.0 milliliters. 25.0 milliliters. And every 1,000 milliliters is 1 mole of KOH. And every 1 mole of KOH reacts with 1 mole of HCl. And this is 0.45 moles per 1,000 milliliters, or 1 liter. Every 0.45 moles is 1,000 milliliters. So if we take a look here, the milliliters will actually cancel out. All the 1s cancel out, and we take 25 divided by 0.45. And we get 55 milliliters. Actually 56 milliliters if we do significant digits correctly. 56 milliliters. Easy enough. If you find this too difficult, you may want to wait until to finish up these problems. You may want to wait and watch the next step, because there is an easier way to do that, and that is with what's called the titration formula. And you're going to be able to use that for any of these problems down here that have the molarity given. So let's take a look at that titration formula. Got this the ma va over ka equals the mub verb over kub, where the c is the coefficient. And this should look very similar to the M1V1, except for here we have the molarity of the acid times the volume of the acid divided by the coefficient in front of the acid is equal to the molarity of the base times the volume of the base divided by the coefficient of the base. So again, you do need a balanced equation. Well, look at this. They didn't give us all names, but hydrochloric acid, that's kind of fun. So we need to make sure we understand that that is HCl. Otherwise, we're not going to be able to balance the equation later. This is NaOH, or sodium hydroxide, and that's going to yield sodium chloride plus H2O. Well, that's kind of boring because all of these are 1s. So then we take the Ma, and I'm going to do it like I always did in class. This is the Va, that's the volume of the acid, is neutralized by 40 milliliters of base. So this is the Vb, which is the volume of the base. And this is the Mb, which is the molarity of the base. Now the coefficients for each of these, the acid and the base, that's the Ca and that's the Cb. So you actually have to, if this isn't balanced, you would actually have to put those in there. So then we simply fill in the problem. We are looking for the concentration of the acid. And don't get confused, this is the coefficient, not the concentration. You know concentration is molarity. So we are actually looking for Ma. And we know that Ma is going to equal Mb verb times Ka divided by Va curb. So then we can take and fill those out. The Mb, the molarity of the base, is 0.10. Actually, it's 0.010 molar. The volume of the base is 40 milliliters. Since my volume of the acid is in milliliters as well, I don't have to change that. If one were in liter and the other one wasn't, then we would. The Ka, that's the 1. That's the coefficient of the acid. There are no units for that. The Va is the volume of the acid, which is the 30 milliliters. And the Kub is the coefficient of the base, which again is not a factor here. So 0.01 times 40 divided by 30.
It's about 0.01333.
0.013. 2 significant digits or 3? Looks like 2 based off of this. And I actually cut one off of that. So everything is going to cancel out except for molarity. And that is the molarity of the acid, HCl. You can do it either way you want. I'll tell you, this is a lot easier. Just to note that this is sulfuric acid, so that's going to be diprotic, and you're dealing with sodium hydroxide. So the Ka and the Kub are going to definitely be different in this one. So make sure you take that into effect. And after you get page 12 and 13 done, go ahead and upload it. And then work on the titration laboratory that deals with this exact math that Mrs. Cotton has so graciously videotaped herself doing. Thank you, and as always, check office hours if you have any trouble with these problems or other things, if you're having trouble submitting or something like that. Excellent. Take care.